Loud. That's quite loud. 1 second to turn it down now. All right, how's everybody doing? Today we're just gonna. Oh, I think I just got blurry. All right, so today we're going to be continuing on with what we talked about last time and the time before, which is what? Review, testing to make sure everyone's alive.
Concepts.
Yep, concepts. And so, what was the theory of concepts that we were talking about in the last two classes? Anyone remember what it was called?
Classical.
Yeah, classical theory of concepts. Classical. And we said that according to the classical view, what is a concept, or what is a concept like? Definition, yes. So classical view, it's just a definition. And using definition, using the fancy terms we used last time, a classical view of concepts gives the necessary and sufficient conditions for being or for the concept applying. So the idea is that to be an example of a to be an example of a quadrilateral is to be something with four sides. Every thing with four sides is a quadrilateral, and to have four sides is sufficient to count as a quadrilateral. That's the example, or that would be like a classic case. Now, we talked about three and then pointed towards four problems with the classical theory. What were these? Or I will write them up and then I will ask you all to explain what they are. So what was one of the problems we talked about? Anyone remember?
Plato's problem.
Yeah, Plato's problem. And which one was that? Anyone remember?
Most concepts don't have definitions.
Yeah, that's the basic idea. Any concept, most concepts you come up with don't have a definition that you can lay out. So, a square, you can say it's four sides with four equal sides with four right angles. However, what's a bird? Give me the definition of a bird. Most people can't give those sorts of definitions. And then Holland says ignorance, and then Cassidy says fuzziness. How does one actually spell fuzziness? I don't actually know. Is it a Y or is it an I? I'm just going to do this.
I believe it's with an I.
Okay, well, whatever it is, we're putting it this way. So ignorance, what was the idea with ignorance? Anyone remember, or anyone want to give it a stab? The idea with ignorance was basically one of the things our concepts are supposed to be doing for us is allowing us our thoughts to be about the outside world. So for instance, it's because I know that a square is a four-sided shape where each side is equal and it has four 90-degree angles. To have a thought about something and think it's a square is to have a thought about anything that falls under that definition. And that's like the way my thoughts are able to be about what's going on out there. However, when you actually look at the sorts of properties we associate with a concept, it doesn't actually allow our thoughts to differentiate between things. So yeah, how can we have thoughts about things we have weak or uninformed definitions about? So how, or as Lino says, we find ourselves are not clear on the concepts, even though we seem to have knowledge about those things. So it seems like the classical view doesn't give us an account for how our thoughts can be about things out there, because very often our understanding of what a thing isn't enough to differentiate it from everything else. The fuzziness issue, this now looks like fuzzy-liness, but whatever. The fuzziness issue was what? Well, it seems like on the classical view, everything either is or is not an example of a concept. So you're either a bird or you're not a bird. However, it seems like as a matter of fact, when we look at cases, we have fuzzy judgments in certain sorts of cases. Is a carpet a piece of furniture? Well, if the definition of furniture is necessary and sufficient conditions, a carpet either is or is not a piece of furniture. But if you actually look at people's judgments, when you ask someone, is a carpet a piece of furniture? People kind of go, I'm not really sure if it's a piece of furniture or not. All right. So those are the three issues we talked about last time. I now want to start off this class talking about the last one, the last issue, which is the one that we briefly touched on last class, and which is going to lead us into an account or into the second picture of concepts that is common in the literature, especially in psychology. So these are what I called, or we will be calling, typicality effects. So what is a typicality effect? Well, the key word here is typical. What is something to be what is it to be typical of something?
Maybe like usual.
Yep, that's exactly it. To be typical is just to be usual, or to be a good example of it, or to be ordinary or common. All of these are really good. So the idea with typicality effects is basically the way this worry goes is if you actually look at a set of necessary and sufficient conditions, so long as something falls under that definition, it automatically counts as an example of that thing. And there's nothing to be said. You can't be a better or a worse example of that thing. So for instance, which of these is the best example of a square? Imagine, like, I'm stipulating, I can't draw perfectly, but they all have the same length. And they all have right angles. Which of these is the best square? Which is the best example of a square? Yeah, it seems like all of them are equally good. It doesn't really make sense to speak about all of them, one being a better square than another one. They all fit the definition of a square, so they're all equally good examples of a square. And why? Well, because our definition of square is 4 equal sides, 4 right angles. So each one of these checks off both definitions. So this one, check, check. This one, check, check. This one, check, check. So no matter, because it's the definition is giving necessary and sufficient conditions, as long as you meet those conditions, you're an equally good example of it. There's no such thing as being a more or less typical example of that concept. The concept applies equally well to everything it applies to. So the reason this is an issue is because if this is how our concepts are, what we should find is, just as with our square concept, or if all concepts are like this, then just as in the case of squares, we should find that anything that is a bird, we all say it's either a bird or it isn't a bird, and any bird is an equally good example of a bird. Or fruit. No matter what it is, you're either a fruit or you're not a fruit. And if you are a fruit, you're all equally good examples of fruit. So what is the issue? What did people starting in the 1960s and 70s actually find in a lab? Well, do we all think that all birds are equally good examples of birds? No. So just to bring this up, every once in a while I like to pull up pictures. Let's go through this. How good, if you were to grade on a scale of 1 to 7, how bird-like is this bird? So 7 being the most bird-like, 1 being the least bird-like. Here's a bird. We've got some fingers. Yeah, everyone feels 7. What about, okay, so here's another easy one. What is this on a scale of 0 to, yeah, 0. Everyone's get the feeling 0. But then what about this guy? Like, if you have to say, how typical is this of birds?
4.
So some people do have the feeling Conrad has, which is it's still a 7. But many people start to feel like it's a bit less good of a bird. These little guys, people generally aren't as high as the full 7. And so this is when you actually look at, also, kiwi birds are my favorite birds. Look at how stupid looking that little thing is. It is so, have you ever seen what a kiwi bird's wing looks like? Look at that tiny little wing. You can't even see it. It's hidden under its fat little bird body. It's just so dumb looking. All right. Anyway, yeah. So when you actually look at how people feel about these things, what you find is that people do have different judgments about these things. So it seems like not everyone just simply says like, oh yeah, a kiwi bird is like exactly as much of a bird as a canary is. Instead, people have different judgments. And it's not just that they have different judgments of typicality. These typicality judgments are correlated with other things. So it's not just that like this is a strange effect. It's also that if you ask people in a lab setting, you give them a picture of a bird and you say, is this a bird? The speed with which they answer is going to be faster with the more typical the bird is. So if you show them a picture of a canary, the speed with which they hit a button, yes or no, is faster than if you show them a picture of a kiwi bird. I mean, we're talking fractions of a second, but when we're talking about brain processing, that's pretty big. Also, if you show them a picture of a canary and ask them to respond as quickly as possible, is this a bird or is this not a bird? They're correct more often of the time than if you show them the kiwi bird and ask them, is this a bird or not? So all this is suggesting that it's not really just a definition in our head. It's not a set of necessary and sufficient conditions, because if it was, we wouldn't see these typicality effects. Rather, the fact that there are typicality effects and that we don't treat all instances of a concept as quickly or as accurately suggests that what's going on in our head is not a set of necessary and sufficient conditions. Something else is going on in there. So does everyone understand just the general gist of this final argument? And really, of all the arguments against it, this typicality effects one is in some ways, sociologically speaking, it's really the one that drove people away from the classical theory strongly, because it led into a new theory. And it was also one of the first ones, like the first ways in which the classical theory was attacked in a laboratory scientific setting, where we could really point to it and be like, concepts are supposed to be the building blocks of thoughts. Therefore, our view of concepts needs to reflect the way we actually think. And hey, put people in a lab setting and they do not behave like they have classical concepts. They behave like they have something else in their heads. So given this on the classical view, given the problems with the classical view and given these typicality effects, what was the view that people looked at the typicality effects and said, we need a new version of how we conceive of concepts. We need a new understanding of them. Given what the reading was, what was the name for this new version of concepts? Prototypes, yeah. It's prototype theory. So basically the way you can think of prototype theory is it was the first real view that was put forward as a full theory of concepts to replace the classical view. And so first off, what do we mean by a prototype? Have you ever heard this prototype theory? So just generally speaking, what's a prototype? You sometimes hear it in the context of like inventions and things like that. Yeah, it's the first version of something. So the prototype of like, I think like a classic version is in like the first Iron Man movie, all those like many years ago. It's like that first robot suit that Tony Stark builds in like a cave out of like boxes. That was his prototype. And then the rest of the Iron Man suits are the versions off of that. So the prototype is something which captures all the key features of everything else that follows or everything else that's inspired by it, but it's not necessarily the exact same as all the ones that come later. So in the same way, a prototype theory says what our concepts are kind of like the rough draft or the core idea, but they're not necessarily going to share all their properties with every sort of thing. So the way to think of what the prototype theory says is that its definition of something like a bird is not going to be a set of necessary and sufficient conditions. It's rather, you can think of it as a list of likely but not necessary conditions. So on a prototype theory, what sorts of properties goes into the the prototype bird or the concept bird, what sorts of things would we put in here? These are going to be things that we associate automatically with birds, but not every bird has. Wings. So yeah, there's one, wings. And so every bird, not necessarily every bird has wings. For instance, that kiwi bird, those little stubby things are so tiny, you could argue that those don't even count as wings. Another things are, so we've got things like inward ears. We've got things like flight, feathers, nest building. And so basically all of these are going to be characteristics that we commonly associate with birds, but that aren't necessary in the way that like equal sides is necessary for squares. Why? Well, because if we actually look at birds, what we find is, well, most of them have a lot of these characteristics. Not every bird has every single one. So to go with flight, does every bird fly? I've already shown you two that don't. Our dear friend the penguin doesn't fly, and our dear friend the emu doesn't fly. So in this case, but we still want to say it's a bird. In the same way, the kiwi bird arguably doesn't have wings because you can't really see them and it doesn't use them. It also doesn't fly, but we still want to say it's a bird. Penguins don't build nests, or at least many species of penguins don't. They either dig, the little ones dig little holes, which I guess you could argue is a nest, but the big ones, what do the big ones do with their eggs? Anyone know? Anyone seen Happy Feet or any other March of the Penguins or any of those other things?
They sit on them.
They just literally put them on their feet and just sit there. So, you know, their nest is their own feet. No, they do not eat their own eggs, David, although that would lead to a quick end of the species. So yeah, also we can imagine, like, if you had a chicken in your backyard and you decide to be the meanest chicken owner ever, or like you kept it on your fire escape, which one is cruel, and then you plucked it so it had no feathers left, it would still be a chicken, even though it's a featherless chicken. So all of these sorts of things. Also, if you look evolutionarily, the line between dinosaur and bird is not at all clear, to such a degree that some people just say the birds that exist today are dinosaurs, and other scientists for other purposes want to say they're not the same thing. But because of this, what you find is the species that fell between dinosaurs and the modern bird had teeth and not a beak. So depending on how you want to define these creatures, maybe birds have beaks, maybe birds don't. So why is this useful? Why is it useful to think of these statistical regularities instead of thinking of them as necessary and sufficient conditions? What does this buy us? Anyone have any thoughts for what it buys us? What is the advantage of saying these are likely but not necessary? So yeah, Marie says they're not strict. And what's the benefit of saying it's not strict? What is the like payoff for a theorist? Yeah, you can be more flexible. So things like why, here's something we want to explain. Why is it that people are much faster to say that a canary is a bird than to say that an emu or a penguin is a bird? Why is it the case? Well, the prototype theory has an explanation. What's the prototype theory's explanation for why we're quicker to say that a canary is a bird as opposed to a penguin?
The canary meets all those features on the board.
Yeah, the canary just simply meets more features. The canary has wings. It has inward ears. It flies. It has feathers. It builds a nest. It has a beak, and it sings. So when you are thinking, like, is this little thing a bird? You very quickly recognize it does, because you immediately find it meets all the criteria. When you're thinking about the penguin, by contrast, what you do is you go, well, yes, it has wings. Yes, it has these inward ears, but it doesn't fly. It does have feathers. It doesn't build a nest. It doesn't have a beak, and it doesn't sing. So it's like, oh, there's fewer criteria that it meets. Therefore, it's faster for me to identify the canary than to identify something like a a penguin or an emu or somebody who's dressed as a bird. In the same way, it also helps you explain fuzziness. How does it allow you to explain fuzziness? And the fuzziness again is a carpet a piece of furniture?
Because it's more flexible, it doesn't necessarily have to be completely clear.
Yeah, because none of these characteristics are necessary. So what you can find is it's theoretically possible to have something with only one or two of these features, and to such a degree that it's like really not clear whether to call it a bird or not, or whether to call it a piece of furniture or not. So for instance, like let me pull up my dinosaur photo. These days, so you know what the velociraptors look like in Jurassic Park, and they look like little lizards? Scientists today guess that if you actually look at the species that velociraptors in the movies were based off of, they looked like this. Is this thing a bird? Well, it's really unclear whether to call it a bird or not. It's definitely a dinosaur, but like it really looks kind of like a bird. Like if I saw that thing running, I would run away screaming, "Oh my God, there's a giant bird coming after me." So like this sort of thing falls on the fuzzy border, and we now have an explanation for that. What do we say? Well, this velociraptor thing does not have a beak. It probably didn't sing. I have no idea if it built a nest, but it's got some feathers. And I don't know anything about dinosaur ears, but let's say it had inward ears, and those little arms it has, I mean, maybe call them wings, maybe not. So why do we get fuzziness? Well, we get fuzziness because something can fall on the border because it only has a couple of the features. In the same way, like virus, is a virus alive? Well, if our definition of living is, gets to reproduce on its own and operates independently of other things, then a virus kind of falls on the border, because a virus cannot survive on its own and reproduce on its own. It needs a host to reproduce, but it also acts in ways independent from its host. So we get this fuzziness here built in. It's like we get it for free. So you can think of it as, we want to explain why we have these fuzzy judgments. We have fuzzy concept judgments, and the prototype theory explains why. It explains the typicality feature. So fuzziness, check. Typicality, check. What are some other advantages that the prototype theory has over the classical? So in this theme, it's okay to remain agnostic on what certain things fall under a concept. Exactly, the idea is that you can remain agnostic in the class. You can't remain agnostic with the classical view. You can with the prototype view. And this is a benefit of the prototype view, because remember, what we're trying to do here is give a description of how human beings actually think. This is supposed to be, we're interested in concepts because we say the concepts are the building blocks of our thought. We want our theory of concepts to capture the way we actually think. And when you look at how humans actually think, we do have degrees of agnosticness or agnosticism in our actual thinking. If you ask most people, is a carpet a piece of furniture? Their answer is usually, I really don't care, but it's pretty, so let's buy it. So as a matter of fact, we are agnostic, and so our theory of concepts should reflect that, and the prototype theory does. But that's a really nice way of putting that, Lena. See what other. It also does a really good job of accounting for Plato's problem. Why is it that we can't give an airtight definition for anything? Why is it that we can never give the necessary and sufficient conditions? Simply put, there aren't any. There's no set of necessary and sufficient conditions. And in fact, remember what we talked about last time with games? Where with games, it seemed like we couldn't define like what made solitaire a game and ice hockey a game and life a game if you're using it in a loose sense. Well, we now have an account of why. It's because our concept of this thing, game, is going to have some features in it, like competitive, fun, multiple people, etc. And why is it that we can't come up with a perfect airtight definition? Because not everything is going to fit all of these. So solitaire will fall under fun, but it won't meet the other criteria, but it can still count as a game. So that's another good thing is Plato's problem. Now, categorization. I'm actually going to save this one for a second, Conrad, because this is really the core strength of the prototype view. Is it gives us such a really nice explanation for how categorization works. That's not only more accurate or more reflective of how humans actually think, but even gives us a way of like spelling it out mathematically, which is something that people really like when you're trying to give a computational theory of mind. The last thing I wanted to talk about, or there's a couple more I want to say. So the last two I want to say is it still gives you a nice account of acquisition, and it also makes more evolutionary sense than the classical view. So first off, how did we say you acquire a concept according to the classical view? What did you do? So for your concept, if it was just a definition, how do you come to learn a new concept? So through your senses, and once you get those things from your senses, what do you do with them? So like you get an experience that looks something like this, and then you somehow end up with a concept square. Well, what exactly do? Yeah, you combine smaller concepts. So you realize, oh, 4 sides. So I just add that in here. I notice 4 right angles added in here. So that was the nice thing about the classical theory, is it explained how we create new concepts and why it's the case that they seem just to build upwards. You start simple and get more complex. Given what we just said about the prototype theory and how it's just a matter of combining parts together to make something that's statistically accurate, or it's statistically accurate characterizations, but not 100% guaranteed necessary characterizations, what will acquisition or learning look like in this case? I'll give you a clue. It's going to look very similar. It'll be some sorts of revision of changing the weights, but learning a new concept is still going to be relatively the same. So remember, our old version of learning what it was to be a bird was just you learn certain things like flies, or you learn things like feathers, bird shape. Well, nowadays, once we go over to prototype, it's still the same sort of thing. Learning bird is still learning things like, oh, it's got features like feathers, etc. The only difference is these are no longer necessary. It's rather that they're more statistical. Also, it's actually, if anything, easier to account for revision, because what you can say is that each property, what you're doing when you learn what a bird is, you don't have to take away things that you learn some birds don't have. You just change the weights around of how much weight you're putting on it. So for instance, your definition of bird might involve like feathers is crucial, the important, and then flying might be the important to you. However, when you start learning, like in your science class, that there are birds that don't fly, but they're still birds, you can realize that, oh, this one's a bit less important, less crucial. So it allows, in some ways, even more flexibility to explain how these things work. All right, this evolutionary sense point. See if I can explain this. All right, so let's just zoom up big picture. You see something out there in the woods. It's a shape. You don't quite know what it is, but you see it like through a tree, and then you get a quick look at it, and what you think you see looks something like this. you see this out in the woods. It's got more stripes than that. It's just my marker's dying. It's supposed to be a tiger, but we can say it's a bear too. Either one works. To serve, what do you need to do when you see this individual out there in the world? What is your first step? You just see an individual that looks like this. What do you have to do? Well, shoot it. But before you shoot it, why do you have to shoot it? Before you even realize you have, how do you realize that you have to shoot it? What's step one?
Assessing the danger.
Yeah, you have to associate it with danger. You need to identify it. So play dead. All of these things follow behind identify it. So the first thing you need to do when you're out in the woods is apply your concept so you know that this thing is dangerous. Step one in avoiding a tiger attack is to know there's a tiger there. But it's not just that you have to identify it. What is the other crucial feature of identifying this thing? If you want to avoid it, what has to be true of your identifying it?
It has to be correct.
It has to be correct. But so you want it to be identify it correctly. But if you identify it correctly, is that alone necessarily enough? There's a second thing. You have to connect it with danger. So that's again going to be somewhat in the identifying it. Contrast these two cases. You've got the person who walks into the wilderness, looks up and says, "Oh shit, that's a tiger," and runs away. Right next to them is their friend who goes, "Huh, is that really a tiger? It's somewhat blurry. Let me pull out my handbook and see. Is that what a tiger looks like?" Let's see. It's got stripes. That thing has stripes. That sharp teeth. That's got sharp teeth. That thing's got yeah. As Holland says, you have to be fast. It's not enough. Like perfect accuracy is not going to be enough to save you. You have to be accurate and fast. If you're not fast enough, by the time you recognize it's a tiger, you are going to be eaten. So when actually we look at human concept identification, what you find is there's a second variable. You have to identify it correctly, but you have to be fast. And as a matter of fact, speed and accuracy kind of are opposite ends of a spectrum. Generally, the faster you do something, the less likely it is to be accurate. And the more accurate you are, the more time it's going to take you. So just think about when you're paper writing or proofreading. If you want to make sure there's no typos on your paper, you want to be absolutely sure there's no typos, 100% certain. How many times should you read over your paper? If you want to be 100% certain. Marie, that is a very practical answer, 3 to 5. But really, the correct answer is you should never stop reading it over because there could be bugs. You could, like maybe the code changed, maybe there's a problem. However, this is entirely impractical. Instead, you want to go with something like what Marie said, 3 to 5, because why? That's a sweet spot right in the middle. You're careful enough, but you still have the time to do it. So what you find is, as a matter of fact, a species that survives is going to want to have concepts that are accurate enough, but also apply quickly. You don't want to have to make sure that you get to 100% certainty before you move on. You want to instead be like, I want to be 90% certain that there's a tiger out there before I run away. Because if I wait until I'm 100% certain, I might get eaten. Even with things like, and with danger, honestly, as a species, generally, you only have to be a little bit like, even if there's a chance something's dangerous, you run away like hell. Because even if it's only a 10% chance, the stakes are high enough, you run away. So prototype theory versus the classical theory in terms of this evolutionary pressure to get close enough to the truth and do it accurately or as fast as possible given that other need. Well, the classical theory is looking for 100% certainty. The classical theory is saying to count as a cat, to count as a tiger, you need 100% certainty on each of the features. The prototype theory, by contrast, has a nice way of saying the way we make these judgments is as long as there's enough features. And those enough features feels more accurate in an evolutionary sense, because as a matter of fact, the organism that gets it accurate enough, or is like, I don't really need to know whether that bird can fly or not to know that I can eat it. Like, all I need to know, if it's a bird, I can probably eat it. Whether it flies or not as important to my eating it. So therefore, it's going to be more useful for me evolutionarily to have a concept that's a little bit fuzzy, or a bit of a prototype style concept. So this makes sense to people of why it would be the case that evolutionarily we don't need the sort of 100% certainty that we need in mathematics. Instead, we just need to be good enough to survive long enough to make babies, which at the end of the day is how evolutionary pressures work. Like, as long as you get to breeding age and reproduce, then you've, in some sense, from the evolutionary perspective, succeeded. I.e., this is something that is going to be able to be reflected within your species' evolutionary history. All right. So the last thing was the one that Conrad, I think, brought up, which is, I'm just going to erase these other ones over here so we can talk about the categorization. So, according to a prototype, how does categorization work? What is it you come across a new individual, you've never seen this particular individual before, and now you want to figure out, what is this thing? Or more accurately, imagine you're asked the question, is this a cat? So what would you do? What would you do to compare, is this a cat? Yeah, you come up with the probability that something fits into the category. And how do you do this according to the prototype view? There's literally a math equation for it that people have put forward. So it's basically, what you do is you just look at the thing you're looking at, come up with its criteria, look at the defining criteria of the particular individual you're looking at now, and then you just compare the two. So let's just come up quickly. What is our definition for a cat? What would be a prototype view's definition for cat? Let's just put it up here. Again, there's not going to be, has a tail. What else do we got? Meows. Whiskers. Paws. Pointy ears. Fur. All right. So, let's say this is our definition, and now we come across this thing. Let me see if I can pull this up quickly. So we're, just going along on our everyday business, and all of a sudden, you see this. You've never seen one of these before. We now have to ask, let's just name this thing. I don't know, what's a good name for this grumpy looking creature? Somebody come up with a name for it, just so we have something to go with. Mr. Ugly. All right, so we come across Mr. Ugly. Now, looking at Mr. Ugly, what characteristics does Mr. Ugly have? Looking at Mr. Ugly, what can we put down here? Got the pointy ears. Pointy ears. What else have we got here? Wrinkles. So wrinkles can go here. Wrinkles. Hair. No hair. No meow. It's too grumpy. No hair. It's got paws. Paws. Whiskers. And it may look like a worm, but it's got a tail there. You see that like wormy looking thing? So it fits the criteria of tail. Tail. So we also have some others here. We have cat-shaped head. So let's actually put cat-shaped head on both of these. Head. Cat-shaped head. So now we're trying to figure out, is Mr. Ugly a cat? Well, we can now say like this is how our brain processes this question. What it does is it calculates the following mathematical formula. And what I want to do here is just put up the mathematical formula to show the way in which psychologists and philosophers and scientists in general can make very scary looking formulas for very simple things, just to show one, don't be scared when you see formulas, because very often they mean something very simple. And two, highlight that the reason we should care about these things is that the fact that you can put in a mathematical formula means you could run it on a computer, which matters for the reason of, we said a few classes ago, what happens if we think of our minds as a computer? So this is the mathematical formula. I can't remember what page it's on, but it's just this. All right, so what on earth does this mean? Why do we care about it? What is the mathematics behind this? Well, what this is saying is the way you tell whether Mr. Ugly is a cat is you just see how similar these lists are. Oh, there's a glare. Give me 1 second. See if I can get this. I might have to shut off the main light and find a different way of doing this if it's a glare. My markers are dying and I can't find my other markers. Give me 1 second, Holland. Let's see if this works. Can people see the screen? Is that visible? Is there less glare? Can it be seen? I mean, I know this look, okay, good. Then I'll just teach in the dark like this is, I can also do little like finger puppets this way. But all this is saying is each character is, yeah, I'll read it out. So it says similarity, SIM of I, comma, J. So I is in Ingrid, J is in Jacob. And so what this is just giving a definition of this. And all this definition is this is a lowercase af of I. This is a symbol from set theory in math, minus bf I minus j minus cf j minus I. So that's what it says. Now, what the hell does this mean? This is a really fancy way of saying, to see how similar two things are, all you have to do is see how many things they share, how much the list shares, then subtract how many things only list I has, and then subtract from that thing how many things only J has. The more similar something is, the higher this number will be. So as a matter of fact, the way we'd run this calculation would just be, well, let's see, how many things are shared on these two lists? Yeah, it's on page 30. Thank you, Grace. I couldn't remember the page. Well, they both have tail. So that would be one thing they share, no meow sharing, whiskers shared, paws shared, pointy ears shared, fur not shared, cat-shaped head is shared. And then how many things does this list have that this one doesn't? Well, 1, 2, and this has 3 things. So to figure out how similar Mr. Ugly is to a cat, we just have the number 1, 2, 3, 4, 5. So this is 5 minus, this has 2 things that the other one has, minus 2, minus 3. And what this gets us is a number of 0. Now, as a matter of fact, if you think of what 2 things that have nothing similar to each other would be, it would be a very large negative number. So what this is just a mathematical way of formulating how it is that we identify whether Mr. Ugly is a cat. And what we do is we just see, what is Mr. Ugly like? What is a cat, our prototype cat, like? Is Mr. Ugly similar enough to the prototype cat to count as a cat? And what this allows us to do is we can now ask scientifically measurable questions of how similar do things have to be to the prototype for us to say they're examples of it. So for instance, if I show you a dog, I first ask you, give me your prototype of a cat, or what is a cat? And you give me this list. And then I ask you, and I just start showing you, like, characterize this picture of a cat. Characterize this picture of a cat. Characterize this dog. Characterize this baby donkey. Characterize this rock. And over time, what we find is we can begin to measure, well, how similar does something have to be to the prototype before a human being is willing to say, yes, that is a cat. Yes, that is not a donkey. And so what this allows for with this fancy formula is we can now actually test people and begin to understand how the human mind categorizes things in a scientific way that you can measure. And you can now apply, like, if we were designing a robot that we wanted to categorize cats, well, all we have to do is know the similarity levels between a Mr. Ugly and a cat. And now we can begin to make predictions about these things. So does everyone understand, like, it's not just that it gives us an account of categorization, it gives us an account that matches what we actually seem to do, and that you could plug into a computer and get to run a program to get it to work. So let me just scroll down and see what else is here. And not only that, this mathematical formulation explains all the features that we saw in those sorts of prototype experiments. So things like speed, accuracy, why are we faster to identify that a cat with hair is a cat than Mr. Ugly? Why is it faster? Well, there's less difference between the list. And if you look at two things that look similar, it's very quick. Just be like, oh yeah, those two look the same. Why are we more accurate at identifying that a haired cat is a cat than Mr. Ugly is a cat? Well, again, there's a lot more in common. It's just quicker. Why do we get the typicality effects? Why is it that we see that we're much more likely to say a haired cat is a good example of a cat than Mr. Ugly? Well, it just scores higher on our similarity scale. That's all there is to it. Why is it that we'd still be willing to say a tailless cat, a cat that got its tail chopped off, is still a cat? Well, it fits enough of these other criteria. It's just a really nice, simple, straightforward account of why it is we categorize things we do. And at the end of the day, categorization is one of the key ideas of why we posit concepts in the first place. All right, so any more things that anyone wants to say about the prototype theory? So yeah, prototypes will have a super high score on the similarity test because it's basically asking, it's similar to itself. And the more an individual is like the prototype, the higher it will score on the similarity scale. So a cat, like, picture your perfect cat, like your ideal house cat, what it looks like. It's going to meet almost all these criteria. It will have fur, it will have pointy ears, it will have paws. And because of this, you are going to be able very quickly to identify that it's a cat. Well, contrast that with, a dog that's dressed to look like a cat. Well, for one thing, you might accidentally call it a cat, even though it's not. And it's going to take you a lot longer to identify, like, is that dog that's in a strange cat costume really a cat, or is it not a cat? Well, you have to compare all the differences. It'll just take your mind longer. So it's a way of saying, like, to be clear, this view is not that at a conscious human level, you're going through these tests. It's rather that it's programmed into your head to run these sorts of calculations. And so what you do when you see something is you immediately run this sort of test. And you can explain how the test works and why it comes out the way it does. Any other questions on this prototype theory? Because prototype theory is fascinating as like one of the most, there are still many prototype theorists, especially I think in psychology, and even people who think prototype theory has some problems with it, which is what the focus of next class will be. Most everyone's, or a lot of times, because it's so calculable, people will still use prototype theory as a core for studying conceptual acquiring amongst children and these sorts of things. It's, even if it's not perfect, it's still a very useful model for understanding how people think. Any other questions on this? Just what prototype theory is, why it has benefits over the classical theory, anything like that. All right, I'm gonna fall asleep if I don't turn the light back on. And good news, we're not gonna be using the board, so give me 1 sec. All right. Any last questions on prototype theory, feelings, thoughts, concerns, anything?
So quick question for the categorization. So essentially the whole point behind categorization is that it allows for computational thinking.
So the idea is, yeah, the way in which any theory of concepts is going to have to account for categorization, because that's something all human beings do. If you give even a baby a dog and ask, is this a doggy or is this a kitty cat? They're going to be able to do it. So we want to be able to explain this and how the human mind does it. And one of the advantages of the prototype theory is it's very easy to explain how this would happen computationally. And if we want to say the mind is computational, then this seems like a big check mark for the prototype theory, because we can give a perfect mathematical characterization of what it is to calculate whether this is a cat. It's just like and generally the more you can if you begin with the assumption that the mind is does computations, then anything that you can make more computational is going to be a benefit of that theory.
Okay, thank you.
Any other things people want to say positively for prototypes, negatively, questionly, anything on this front? All right. Well, then I'm going to officially class is over because this is all I had to cover today. But I do want to briefly keep up with the saying what next class is going to look like and what we'll be doing. So if you want to get going and want next class to be a surprise, feel free to go. If you want to stick around, feel free to stick around, because I'm going to talk about what we're going to be doing next class. No pressure one way or the other. I'm going to erase the board, and when I come back, I'll start talking again. All right, so have a good one, everybody. So basically, we're next class, just like with the classical theory, we're now going to talk about some of the issues with prototype theory that there are. And there's basically 4 issues we're going to talk about. There's more of them overall, but we're going to talk about 4. One is that we're still going to run into ignorance problems. It doesn't seem like the ignorance problem, same sort of problem that applies to the classical theory, applies here. Because even if we're saying that it's just a statistical characterization of properties that make something an example of that concept, there's still going to be a case of we're going to have concepts where we even are going to have the same concept for our smallpox and measles concepts are still going to be similar enough that even if we say it's statistical, you should read, just read the second part of what you were supposed to read for today. So the only reading for next class is just to, it's not anything that I didn't assign for today. It's just basically from page 32 to, where is it? 32 to, where does this end? 32 to 43 is what we're going to be talking about next time. But don't worry about like super detailed stuff of like, the basic idea is just, you don't have to worry about these little computational partial representational things on page 40. It's just more going to be the core ideas of what the issues are. So the first one is ignorance, same worry applies as in the classical view. The second issue is so this next one is we get typicality judgments even where we shouldn't get them. So what I mean by that is that when you actually look at, so one of the ways in which the prototype theory motivates itself is that it says we have an explanation for these typicality judgments. Our explanation is that the way we judge whether something is or is not a member of the category is the very same set of criteria we use to judge its typicality. So when we judge that this is a bird, we're doing the exact same sort of calculation as we do when we judge, is this a typical example of a bird? It's just we compare these lists. Well, if this is right, then what we find is those handful of categories that are mathematical and that actually have necessary and sufficient conditions shouldn't get typicality judgments, because we all know that an even number is an even number. It's one of the few cases in which whether there shouldn't be anything as a typical or more accurate portrayal of an even number. Because, to be a good bird, you have to meet as many of this list as possible, but there's only one criteria you need to meet to be an even number, divisible by 2. So every even number should be just as typical of an even number. But if you actually ask people in a lab setting, they say that 2 is a more typical even number than 8,700,444. Like, that's not something that should happen according to the class or the prototype theory. So the argument goes that, well, if this is the case and we get typicality judgments, even in the cases that prototype theorists say we shouldn't, then typicality judgments don't show anything about our concepts. They show nothing. It's a red herring. We need to ignore it. And we still need to account for these, but we need to do it in some other way. 3, missing prototypes. The issue with this one is basically that if the prototype theory is correct, then every single concept should have a prototype associated with it. We should be able to give the criteria that categorize that thing. But if you actually look at some of our concepts, especially complicated ones, what you start to realize is we don't really have a prototype that goes with it. So examples are things like the typical American town. It's like, well, what exactly? I don't think I have a prototype that goes with it. I will say like the typical American, but that doesn't seem like it's something that has a core thought to it. This one is a little wishy-washy, so I'm going to explain it more next time, but that's the general idea, that we don't have, there are plenty of concepts we have that we don't seem to have a prototype for. So therefore, a prototype can't be a concept. And lastly is compositionality. It seems like one thing we do with our concepts is we stick them together. So for instance, we have a concept fish and we have a concept pet. And so according to the prototype theory, there's a prototype of what a fish looks like. I don't know. What's your prototype fish? Maybe a goldfish? I'm just going to draw like a little Christian symbol because it's easier. And we have a definite, like a prototype for what a pet is. And it's going to be like a cat or a dog or something like that. But we can also form the concept pet fish. Well, what is a pet fish? What is our prototype for a pet fish? Well, it seems like our prototype for a pet fish is not just a combination of our prototype for pet and our prototype for fish. A classical theory would have an easier time explaining, well, what's a pet and what's a fish? Well, our definition of pet is like animal owned by a human. Our definition of fish is whatever our definition of fish is. How do you define pet fish? You just smush them together. Looks like a prototype theory has a much harder time, because if your definition of, or if your like prototype of a pet is cute, furry, soft, buy at pets or snuggles with you, then how on earth do you get the concept pet fish? How can you combine pet and fish when your or at the very least, if you were to combine the prototype for pet and the prototype for fish, you wouldn't get what we actually get, which is like the image of a goldfish. The prototypical pet fish is not what you get when you could just combine pet and fish. So then how on earth do we explain these compositional combinations? And compositional here just means combining two parts together to get the nature of a whole thing. And so it looks like one thing we do is we combine our concepts together. And while the classical theory had a rather straightforward explanation for how this would work, the prototype theory, it's much more difficult. And this is really one of the major worries which has led people away from the prototype theory in certain areas. We'll come back to this one more next time, a lot more. But if anyone has any questions about these things now before the reading, I'm here for another, I have nothing to do for another 35 minutes. So feel free to keep asking. Any questions, comments, concerns, feelings on this? If not, you are all welcome to go. I'm going to stop the recording. And so if anyone wants to stick around, feel free to stick around.